We introduced binary trees last time, where binary trees are trees. The name comes from the fact that we can have one node with at most 2 child nodes. Binary trees. We're going to extend that to binary search trees. Before we do that, anybody have questions? Any open questions that need to be addressed? Or just any questions about anything before we get into content? Yep.
I took you up on the challenge. I implemented I implemented the depth source search in, I think, pre-order without using any stacks.
Nice. Was it painful?
No, it's 23 lines of code.
Oh, nice. Yeah, I'd like to see it. I have to increment my number. I think that's 6 now who've taken me up on the challenge. But yeah, it's in still 26, you said?
26.
So 26 versus 5. Still a lot more, but yeah, that's pretty
22.
low. 22, yeah, that's pretty damn good. All right, anything else before we get into content? Let's do it. All right, binary search tree in one slide. This is what they are. Binary search tree, and I'm going to use less than and greater than in my explanation and then correct myself in a bit. But a binary search tree is a binary tree with the properties where every value to the left of a node is less than that node's value. So everything to the left of this node with 5 is less than 5. Everything to the right of a node, all those nodes, or the right subtree we say, has a value greater than the value at that node. And this property has to hold for every single node in the tree. So with the root, everything over here is less than 5, greater than 5. And at this node, everything's less than 2, greater than 2. For this node, everything's less than 8, greater than 8. A few caveats. I'm going to say less than throughout lecture and greater than, just because I don't feel like saying the whole thing every time, but it's comes before according to a comparator or comes after according to a comparator. And I'm going to assume we use the less than comparator, and that's what I'll use in my examples. But we do use generic comparators where everything to the left technically comes before the node's value according to a comparator, and everything to the right comes after that value according to a comparator. It's a lot easier to say less than, greater than. And just knowing that that concept applies, even if we don't have the less than operator with integers, we can sort anything in any way, just like we could with insertion sort. Same thing here, but just to keep the words down, it's easier to say less than comes before this value according to the comparator. It's just a lot of extra verbosity. And the other caveat is ties. How do we handle ties? If I want to have 2 5s or 2 2s or 2 8s in this tree, how do I handle that? And that's really up to the implementation, up to really the reason why you're using a BST. You have some project, you use a BST. That reason is going to determine what you do with ties. Sometimes you don't want to allow ties at all. If you're using a BST to create a key value store where you sort based on the keys of that data structure, and then each node knows the key and also the value, which is a common thing to do with these trees, then you would not allow ties at all. We don't want to allow ties in our key value store. We don't want duplicate keys. For our purposes, for this lecture, we're going to break ties to the right, just an arbitrary decision. When we're talking about the concept of a BST, we don't really have any specific application that's going to care what we do with those ties. So I'm going to break ties to the right. Just arbitrary decision. I could break them to the left, that'd be fine. But if we insert 5 into this tree, it's going to go over to the right subtree. So with those caveats, that's the definition. Everything to the left, less than. Everything to the right, greater than. And that's a BST, binary search tree. It's so any BST or any binary tree can be a BST if it has these properties. And our goal for this lecture is writing a BST class that's going to maintain these properties when we're working with the tree. We're going to use generic types and a comparator for that generic type. So our BST of some generic type takes a comparator, much like our sorting class when we had insertion sort. We're going to have anything. We can sort absolutely any value, as long as it's not a primitive. I always have to put that caveat there, by any order. Whatever comparator we give this, our binary search tree is going to work with any type and any comparator for this sorted order. For a class, we're going to use integer and less than operator. to sort integers in increasing order, just the natural way of sorting things, because we've already talked about comparators. We don't have to get bogged down with that. I'm going to focus on BSTs today. And the class is going to store that comparator from the constructor so we can call it whenever we want, and have a binary tree node. So this has a binary tree as an instance variable, or rather a reference to the root of a binary tree as an instance variable, and that's initially empty. We know from doing task 3 and working with linked lists that our empty node-based data structure, we're going to set that equal to null for our purposes to indicate an empty data structure. Then we're going to have if root equals null all throughout our code. And we want to write 2 methods here, insert and find. That's what we're going to do the majority of today's lecture. How do we insert into a BST while maintaining the property of a BST? So we want to insert without breaking that property. If we insert into the wrong place in this tree, we're no longer going to have a BST anymore. If we insert in a place that doesn't maintain for every single node, left is less than, right is greater than, then it's not a BST and everything breaks and we lose all the benefit of using a BST, which we'll get to at the end after we define these 2 methods. I'll talk about why we would even use a BST. I'm motivated after talking about the content. And then find, which is going to leverage that property. We're going to find values in this BST, taking advantage of the fact that everything to the left is less than, everything to the right is greater than. And we're going to be able to find very efficiently in this tree. How do I minimize suffering while traversing? I don't know if I can help with that. Hi, tomato. Just embrace it and enjoy it. It's fun. It's fun stuff. And here's the usage of a BST. We're going to create a BST, specify the type. I'm going to just say integer. And the comparator, I'm going to create a new instance of int increasing, which is going to extend our comparator of integer. Same stuff we did through inheritance. And implement the compare method to be the less than operator. Our default sorting with integers is going to give us the default sorting of increasing integers, how we would expect integers to be sorted. As opposed to last time we did int decreasing, all we did was use the greater than operator here instead of less than, and got our int decreasing. And then we got our ints sorted in decreasing order. But the point is we can sort anything in any way. We can swap out this comparator with anything and get a different order of these ints. Or swap out ints for something more interesting and sort whatever we want. And this, we're going to insert all our values and then try to find 7 and 8. Those are in the BST, so we expect those to return true. Find 3. 3 is not in this BST, so that should be false, so we should get true, true, false. And we're going to run an in-order traversal on the root of the tree to visit all the nodes. This is the structure of how we would use this, except if I could change one thing on this slide and go back, change this to bst.getRoot, and getRoot, call the getter instead of accessing the value directly. The assumption is this code is in the binary tree node class. I don't like that assumption. That we would call getRoot there. Or no, it isn't. Man, I'm still backwards. It would be in the BST class. Root is an instance variable of BST. Actually, yeah, I'm not that mad at that. All right, so any questions on what we're trying to do, which is implement insert and find to get the expected behavior that we want here while maintaining the properties of a BST? Let's do it. So here's insert. We want to insert a specific value into this BST, and we need to find where to put it. With insert, we need to insert into a place that's going to maintain the property of our BST. Our BST, we're going to assume when insert is first called that it is a BST, that everything for every single node, everything to the left is less than, everything to the right is greater than, assuming the less than comparator with ints. And then we're going to insert into a location that doesn't break that property. We need to find a home for this new value that's not breaking the property. And if calling our insert method is the only way you can add anything to this tree, then we're always going to maintain that property because this method doesn't break it. the tree starts off empty, we're always going to have that property if our insert method does what it's supposed to do. So we start off by checking for null. We'd like to have these null checks. If a null means that our data structure is empty, then we want to check for that first. Before we ever call the dot operator, if we start going through this thing and start saying this.root.getValue, we're going to get a null pointer exception. Everything breaks, program blows up, everything stops working. So we want to check, is this null? Because if this is null, that means it's empty. And if the tree is empty and we're trying to insert something into it without breaking this BST property, the decision's pretty easy. We have an empty data structure. We're going to set the root equal to a new node with the value we're inserting. We now have a data structure of size 1 where the root is the value we just inserted. Not much work to do. It's an empty data structure. Just put it in the only place that you can. It is now the root. So that one's easy. But what happens if the data structure is not null? Well, now we can, in our else, assume that root is not null. If root was null, we wouldn't ever be in the else block. So root is not null. And we're going to set up our recursion starting at the root node, which we're going to immediately call .getValue. We know this dot operator is not going to give us a null pointer exception because node is not null at least at that first call. And we're going to check for null every time we do a check and make sure we're never passing null in this method. And that dot is not going to give us a null pointer exception. This is something, I think this is behind most of you at this point, but task 3, there's a lot of null pointer exceptions for that task. If you're not careful with the way you're handling nulls in your node-based data structures. So just in case somebody still hasn't gone through that yet or is still going through it right now, just to talk about it a little bit, you would, if you have a node-based data structure, linked list in task 3, but it will be a binary tree in task 5. In task 3, you would, if you call getValue, this is most commonly what happens, you call getValue on what you expect to be a node. Usually in your testing, you call getValue on what you expect to be a node, but that node is actually null, and you get a null pointer exception. This happens, usually you write your tests, you submit to Autolab, and Autolab says null pointer exception when running your tests on this incorrect solution. And the problem is the incorrect solution doesn't give you the right solution. It's not going to give you the right answer in at least some cases for some of your tests. If your test is doing what it's supposed to be doing, it shouldn't be always giving you the right answer, which means, say you're expecting a linked list of size 3. So you call linked list, the list that I got from the get ratings, .getNext.getNext.getValue to check the value of that third node in the linked list. And my incorrect solution returned a linked list with 2 nodes. You just call .getValue on null, and you're going to get that null pointer exception in Autolab. So don't ever assume that what you get is what you actually expect. And with the case of these node-based data structures where we actually do introduce null, making sure that you don't have null where you expect a node. And that's true. I don't do much in this class, but out there in industry, in your testing, you usually want to check for null all over the place, or even in your code, depending on what exactly you're doing. Nulls might show up when you don't expect them at all. You don't want your program to crash whenever it sees a null. In Java, anything can be null except primitive values. You could have null anywhere in your code. But especially with these node-based data structures where we're purposely introducing null, make sure that's not null. The quickest way to do this, in JUnit, you can import assert not null. Call assert not null on the node that you expect to be a node. And if that is actually null, the test shuts down right there and says this is an incorrect solution without having any errors. But if you ever make it to the next line after that, that means you do actually have a node. It must not be null, or else that assert would have failed. So then after that line, after that assert not null check, you can safely call .getValue.getNext without getting a null pointer exception. But checking for null, because the incorrect solutions are going to return the wrong thing, sometimes getRatings itself is going to return null. It's an incorrect solution. It's not going to do the right thing. And we have purposeful nulls. Make sure you're checking for those nulls. So I just want to make sure I talked about that. Back to this. We want to set up our recursion. How would you check exactly where you're returning a null node? all the time. In your tests, every time you have what you expect to be a reference to a node in a variable, in a local variable in your tests, make sure it's not null. If you expect it to be null, assert that it's null. If you expect it to not be null, assert that it's not null. You always want to assert everything. Never, ever, shouldn't say never, ever, but don't make assumptions in your tests. Don't assume that what you get from a potentially incorrect solution is actually what you expect it to be. Always assert things. Call your asserts. Assert equals, assert true, assert null, assert not null. Use some asserts, or just use assert true for everything and write your Boolean expressions. Assert true, node equal null. Assert true, node not equal null. It's going to do the same thing as your assert null, assert not null if you don't want to use those. You can use assert true and write your Boolean expressions. But always assert everything. Don't make assumptions. And that's a common assumption. It's just part of the learning experience for task 3. It's part of what I want you to see, is that when you expect something, it might actually be null in some cases, especially with node-based data structures. Or if you want the really simple solution, get ratings, assert that it's not null, and then assert its size. You have a size method. It's given to you. Just call it and assert the size. Then you don't have to do any of those null checks after that first one. Yeah.
So I implemented that in the third one, and then it was still giving no pointer exception. So I eventually had to do a null check. It had the size, but somewhere the reference was set to null. It should be removed.
Okay, I'd have to look at that one. I'd be interested in that one.
That's what I asked you.
Okay, I might have forgot. But yeah, I do want to look into that, because if checking the size isn't doing it, you check to get ratings for null and then the size. It's possible that get ratings return null if you didn't have that check, because there is an incorrect solution that will, if you're removing the first node, just changes the whole list to null. But yeah, I'd like to see that if I have something weird going on there. All right, so let's get back to it. Once the tree does exist, the root isn't null, then we're going to set up our recursion. Our recursion, I want two things. I definitely want the value that we're going to insert, and I already have that here, but I also want to remember where I am in the tree. There's the same thing for linked lists. I want to remember which node I'm currently processing. So we're going to go to the node. We're going to take the node that we're processing and pass it as a parameter. This is the only way that we can get information passed from one stack frame to another is through parameters. Or if we have objects, we can use the keyword this. If we're passing instance variables, we can do it that way like we did to begin with. Otherwise, we need parameters. If we're not in the class, like we're in a BST class, so this doesn't really help us in this particular instance. So we're going to pass the node that we're currently visiting, currently processing, as a parameter to keep track of where we are in the tree. And we're going to navigate this tree and figure out where to insert this value. To find out where we're going to insert it, we're going to call our comparator. And again, I know I'm repeating myself, but node.getValue, this dot, since we made sure root is not null, this is not going to give us a null pointer exception on the first call. And for subsequent calls, we're going to check for null and only make that call in the else of the null. So we're never passing null to this method. Yeah. No. This is a common thing, and it's fine if you do that. A lot of students do that. A lot of programmers in general. If this whole thing, I could do equal true, but it's already a Boolean. It's already true or false. I don't have to add the true. True equals true, false equals true. The truth table is going to give me the same exact thing that I already have. So we're going to ask our comparator, and the question we ask our comparator is, does the first argument come before the second argument? Does it come strictly before? So we're going to invoke our comparator and say, does the value I'm trying to insert come before the value at this node? Or in our purposes, does the value I'm trying to insert, is it less than the value at this node? If it is, I need to be thinking left. I need to move on to the left in this tree. If I'm thinking left, because that's the property of a BST. If this thing comes before the value of this node, it has to go to the left, or else I don't have a BST anymore. If I start going right at this point, I don't have a BST because I'm going to insert this thing at the wrong spot. So I'm going to think left, and if I look to the left and I find null, I already found a home for this value. I'm going to add a new node with the value I'm inserting as the left child of whatever node I ended up at. It might still be the root. I might be 10 levels down in this tree. I don't know. But wherever I am in the tree, this is where this value is going to go. If I don't find null, if the left child isn't null, so there is a left child, an actual node there, I'm going to move to the left through a recursive call. So I'm going to make a recursive call with node being the left child of the node I just checked, and then forward the value that I want to insert. So I'm making my recursive call to move to a new node while using the parameter to keep track of which node I'm currently processing, which node am I currently visiting, which node am I currently asking, hey, where should this value go, to your left or to your right? That's the question I want to ask each node until I find null. Once I find null, that's where I'm going to insert. If the comparator returned false, we're going to think right, and this is where my code ends up breaking ties arbitrarily to the right. I'm going to invoke my comparator one time, and if it returns false, that means the value is either strictly to the right of the value at this node, or it's a tie in value. Either way, I'm going to go to the right. We could check for ties and not allow them. We could break ties to the left. Whatever we do, we got to choose one of the three options. I chose break ties to the right. I don't know why. But we're going to break ties to the right. So we're thinking right, and I'm going to look to the right. If I see null, if there's no right child, I got a right child for it. I'm going to create a new node with the value I'm inserting and set that as the right child of this node because I found a home for this value I'm inserting. Otherwise, set up my recursion and go on to the right child. Go to the right node in the next recursive call. Visually, it's going to look like this. Say I have this tree and I want to insert 7. I'm going to ask a series of questions. Does the value I'm going to insert come before the value at this node? For our purposes, we have the less than comparator. So is 7 less than 5? Does 7 come before 5? And the comparator is going to say false, so I'm going to move on to the right. And I'm going to ask the same question. Does 7 come before 8? Is 7 less than 8? It's going to say true. So I'm going to move to the left. When I look to the left, I'm going to find null. So that's my home for 7. 7 is going to go right there. Then all the recursive calls return. I should just set up more. I always end up doing more examples than just the one. I should just set more up in the slides. But let's say we want to insert 5. I'll get in, yeah. Possibly. The question, will we have to do this on a memory diagram? Possibly. You have to do something for the quiz involving trees and linked lists. So if we want to say, somebody always asks if we want to insert a duplicate, how do those duplicates actually work? So let's do a couple of them. Let's say we want to insert 5, kind of probably the trickiest duplicate. Let's insert 5 into this list. We're going to ask our question, is 5 less than 5? The answer is going to be false, so we're going to move to the right. That's how we're breaking our ties arbitrarily. So we're going to move to the right. Is 5 less than 8? True, so we move to the left. Is 5 less than 7? True, so we move to the left. And then insert 5 right here when we find null. If we want to insert 2, 2 less than 5, move to the left. 2 less than 2, false, move to the right. 2 less than 4, true, move to the left. Find null, and insert 2 right here. Yeah. Yep. Mm-hmm. The concept of a BST doesn't really address ties. It's up to the implementation. Our implementation said to the right, and that's just how we do them. But it is still, if we say our property is everything to the left is less than, everything to the right is greater than or equal, then this node 2 everything to the right is still greater than or equal. And for this 4, everything to the left is still less than. Everything still holds. Yeah?
So if you do it with -3, it would just end up on the right side of -3.
Yep. We go left, left, right. Yep. Okay, any other questions on this? I think the concept isn't too crazy with this one, but it is still another example of recursion. So, and actually, I said this in the last lecture, nobody asked about the recursion, so maybe I'm a little off on this one. But I expect recursion to still be pretty new to everybody. So I would especially expect questions on recursion. Because this task 5, this is where the recursion is going to catch up. That I think most of y'all use loops for task 3. This is where you really, I won't say have to, but you're really going to want recursion. What's up?
After each call, each recursive call,
Mm-hmm.
the current stack gets closed. Because we are not returning it.
I think so. It depends how Java exactly handles tail recursion, but each stack frame should be, that spot in memory should be reused by the next stack frame because it's tail recursive. That's not, by the way, for any of you who are thinking about tail recursion at all, in your memory diagrams, don't do tail recursion. First of all, it wouldn't really be fair to put that on a quiz. But if I do give you a quiz that happens to have tail recursion, still draw out every stack frame, like it's normal recursion, like it's a normal method call. Yeah.
What is tail recursion?
I was hoping I wouldn't open myself up to that question, but I'll do it very briefly. If the last thing that a recursive method does is make a recursive call, like when each call gets the return value from insert helper, it doesn't have anything else to do after that. I'm not 100% sure how Java handles this, but it should, if it's doing what I think it should do, what it'll do is actually delete that stack frame. Since that stack frame doesn't have to do anything anymore, the only thing it's going to do is take whatever this call returns. It returns void anyway, so it doesn't have anything at all to do. But if this returns something, all it's going to do is return whatever this returns. If we have return insert helper and an actual value, it doesn't have any processing left to do. So it can safely be destroyed, and then that memory space for that stack frame can be reused by the next stack frame. So effectively, we only have one stack frame. Even if we have 1,000 recursive calls, only one stack frame will be created. And it actually avoids Stack Overflow errors. We can't have a Stack Overflow with tail recursion. So it's a really nice efficiency thing. It's not something you need to know for 116. I won't require that at all.
But for normal recursion, it is always great to stack frame until it's resolved.
Yep, and it has to. So if I had, like, say this returned an int, and I said return 1 plus, like for our size method for a linked list, return 1 plus whatever the recursive call returns, the stack frame has to still exist because it has to get the return call and then add 1 to it and then return that. So it has some minimal amount, but some processing left to do. So it can't be tail recursive. It has to keep every stack frame on the stack. But if there's nothing left to do, it's just the recursive call with no more processing, and we're not going into the else, like it's either one, it's going to be the last thing that the method does, then it's a candidate for tail recursion. Not something you have to do. And even if you understand that, don't do that on the quizzes if we happen to give tail recursion. If what we write just happens to be tail recursive, don't worry about it. Okay. Let's move on to find. So find is the other side of the BST property. Here, we're not worrying about preserving the BST property because we're not changing any state. We're not changing any instance variables here. But we are going to leverage the fact that the BST property exists. We're leveraging the fact that everything to the left comes before, right after, and taking advantage of that fact to significantly reduce our search space for this method. And it looks very similar to insert, very similar concept for us humans to understand at the very least, that we're going to start off by trying to find a particular value and checking if the root is null. If the root's null, the tree's empty, doesn't matter what we're looking for, we're not going to find it. We're not finding anything in that tree, so just return false. Otherwise, set up our recursion, and we want to start at the root as the node that we're currently looking at, and then passing the value that we're looking for. We're going to ask our comparator, does the value I'm looking for come before the value at this node? Because if it does, I'm thinking left. I'm going to go to the left, and if left is null, I'm not going to find the value I'm looking for. Because if the value I'm looking for comes before the value at this node, wherever I am in the tree, the property applies for every single node of a BST. If the value I'm looking for comes before the value at this node, if it's in the tree at all, it has to be to the left. There's no other choice. It can't be to the right because that wouldn't be a BST. It has to be to the left. So we eliminated everything in the right side of this node. If this is the root, we just eliminated the entire right subtree, and we know we can look to the left. And if the left is null, there's nothing to the left, and what I'm looking for, if it exists, has to be to the left. It's not in the tree. I'm never going to find it. So we can return false. But left is not null, then we can make our recursive call to the left and move on to that left child, which we know is not going to be null because we just checked if it's null. So we know node won't be null in the recursive call, in the next recursive call. And move on to the left and do the same thing. Repeat the process through the next step of the recursion, the next recursive call. And here's where things are slightly different from insert. We're actually going to call our comparator a second time. We're going to call our comparator again, but this time we're going to ask the opposite question. We're going to say, does the value at this node come before the value I want to insert? And if it says yes, then I know that what I'm looking for must be to the right. It has to be to the right. There's no other choice because this is a BST. So if this node's value comes strictly before the value I'm looking for, thinking right, checking for null. If it's null, I'm not going to find what I'm looking for. And if it's not null, I can move on to the right in the next recursive call. And if the comparator returned false both times, so if we ever get to this else, that means the comparator returned false both times. Does the value I'm looking for come before the value of this node? No. I swap them and say, does the value of this node come before the value I'm looking for? And the comparator says no. It's only one more possibility. Those values are equal, and I found what I'm looking for. Or, man, I misspoke. Those values are equivalent according to the comparator, and we can return true. We found what we're looking for. And this is different than equality. Whenever we have a comparator, we're not checking if two values are actually equal. They are the same order according to the comparator. It's a subtle difference, but it is a big difference. Whenever we're working with a comparator, we're never checking like else if node.getValue.equals to find. We never do that when we're working with comparators. We're going to ask the comparator if they're the same order. Because this comparator might not be checking for equality at all. Ours is, it's the less than operator. The only way to get into this else statement is those are the same int. But what if we had a title comparator that ignores case, for example? An idea I just pulled out of thin air, right? Then we can have two titles in ratables that are the same according to the comparator, but maybe they're the same letters, but one's all uppercase and one's all lowercase. Those are not equivalent strings. If you do dot equals on those, it will return false. But the comparator will get you to this true and say, okay, according to this comparator, they're not actually equal, but according to the comparator, they're equal enough that their relative ordering does not matter. This could also be a comparator that compares the magnitude of integers or the absolute value of integers. And I have 5 and negative 5. Those are not equal integers, but the comparator is going to say they're the same relative ordering and get us into this else and say, well, you found what you're looking for. You found an integer with magnitude 5. That's all you were looking for. They're not the same integer, but you found what you're looking for. So it's different. It's the comparator saying two things are equivalent versus actual equality, very different things. So find, in this thing, we want to find the value 4. We're going to ask, does 4 come before 5? Or is 4 less than 5? And the comparator is going to say yes. We're going to move to the left. Is 4 less than 2? Comparator is going to say no, so we invoke the comparator again, swap the arguments, and say, does 2 come before 4? Comparator is going to say yes, so we're going to move to the right. Then to the right, we're going to say, does 4 come before 4? Does 4 come before 4? It's going to say false both times, so we know that we have an equivalency here according to the comparator, and we're going to return true here. So we said, less than, move to the right, greater than, move to the left, greater than, move to the right, equivalent, return true. I only have one of these in the slide, so I'll back up and say we want to find the value 6, just so we can have one that's going to return false. I'm going to say, does 6 come before 5? No. Does 5 come before 6? Yes, so we'll move right. Does 6 come before 8? Yes, move left. Does 6 come before 7? Yes, move left. Did I say right again? I meant left if I did. And then we find null here. Once we find null, we know we're not ever going to find what we're looking for. We're going to return false up the recursion, return false. Any questions on insert or find? Is there a reason to use the comparator rather than checking direct equality? For the this might have been asked before I gave the examples, but for the examples I made, like if we don't care about upper and lowercase letters, we don't want to check our strings for equality because a title versus a title all lowercase versus a title with the first letter of each word capitalized, like proper casing with the title. I want to treat those as the same movie or the same song. So if I do dot equals on the strings, it's going to return false and say, no, those are different movies. One's lowercase and one's uppercase. And we want to treat those as the same. Yeah.
Is it possible to find a value that is in a binary true twice? So if you have -3 coming off of 7, right, would that mess up at all, or would it just say true?
That one would mess it up. So if I had -3 off of 7, that won't be a binary search tree anymore because the property won't hold for 5. It won't hold for 5, right? 5, everything to the right has to be greater than, and the -3 would break it. So the -3 would have to be over here. Or technically it could be over here, but the way our insert is written, it would end up going right here if we had -3 in there again. Because the property has to hold for every single node. But like if we inserted 2, we insert 2, it's going to go right here. And then we try to find 2. As soon as we get to this 2, we're going to return true. And the existence of that next one won't matter for our find algorithm. Yeah?
So how would you find if you have like 2 of the same number?
The first one that you come across, that's the one that's going to return true. So if we had, what's the other, I forget the other one I did. Like if we did 8, a second 8 is going to go right here. And then we want to find 8, we would go to the right, get here, and then return true right away. We would find this value, and then return true. We never would actually get to that second one. Yeah.
So when you're inserting values, every single value that's greater than 5 is going to be on the right. So it doesn't matter if the fact that it's 7. I mean, the fact that 7 is branching off of 8, that makes sense because 7 is still greater than 5.
Yep. Yeah, as long as the property holds for each node, like 5, everything over here has to be greater than. 8, everything over here has to be less than and greater than. So like if we wanted to add 6, it's going to go right here. And that's perfectly fine because it holds the property at every single node. Or if we wanted to add 5 again, the second 5 would go right here. And that's perfectly fine.
And you said like for the last part of the statement where it compares the 2 things and it doesn't like say it's the same number. But, so that example is when you're finding the value of 4 and it's before there. Or what would be an example of that where it goes to the last?
Like when we found 4. Like,
So that was,
like with 4, we said, does the value I'm looking for come before the value at this node? And the comparator said false. Then we went to the else if, and we said, does the value of this node come before the value I'm looking for? And that also returned false. That puts us into the else. And the else says return true. An in-order traversal of a BST will visit the nodes in sorted order. In-order traversal is going to visit everything to the left first. So if we call in-order traversal on the root, it's going to go to the left first. And for each node, it's going to go to the left, visit the node, and then the right, and visit the root, then visit everything to the right. This follows exactly the definition of a BST. A BST says everything to the left is less than, everything to the right is greater than. So if we're visiting everything that's less than, then visiting the node, then visiting everything that's greater than, we're visiting the nodes in sorted order. And this is where in-order traversal starts outshining the other two, at least for our purposes, because we're only going to see BSTs as our big application of it. We're visiting them in exactly sorted order because in-order traversal mirrors exactly the property of a BST. Yeah. Right. Mm-hmm. Yeah, I got what you mean. Yeah, it's going to visit the lower values, then the value, and then the higher values. Or more accurately, everything according to the comparator, everything that comes before that value, then the value, then everything that comes after the value. And with our insert implementation, after and equal to. So equivalent and the same thing. Which if we inserted 5, the property still holds. By the way, kind of surprisingly, if we insert 5, we break the tie to the right, then go left, left, and insert 5 right here. An in-order traversal goes over here, visits 5, goes over here, makes the left recursive call, makes the left recursive call on null, then visits 5. So those two 5s would still be next to each other, and then visits 7, 8, and 14. So even with those ties, we're still getting sorted order. And up to this point, this is what's important for your homework for test 5, is the bulk of the challenge of that. Pretty much the I don't want to say the only challenge, but the majority of the challenge is taking a BST of ratables that's sorted based on your Bayesian average comparator and returning a linked list of all the ratables in sorted order. So navigating a tree using an in-order traversal and gathering up all of the nodes into a linked list and returning one linked list with all of those values in sorted order. And the rest of today's content, I want to motivate some CC 250 stuff. So any questions on this before we move into that? We don't have a ton of time. Let's do it. So a little bit of vocab first. A binary tree is balanced if the two subtrees for each node have roughly the same number of descendants. Our example today was fully balanced. We have this nice symmetrical tree. Everything looked pretty on the slide. That's not always the case, but if that's the case, if our BST is balanced, we have some really nice properties. The height of that tree, which is the number of steps we need to take to get from the root to any node in the tree, is going to be O of log of n. So log n height to the tree, that's, we say the length of the longest branch from root to the furthest node, log n. Insert and find, each time we have one step of the recursion, we do constant amount of work, and we move down one step, one layer in the tree. And if the height is at most log n, or at O of log n, that's going to be log n time to get to the bottom, even in the worst case. So log n insert, log n find, and for what it's worth, we can sort values in n log n time now. We have n values, create a BST, stuff them all into the BST, and then do an in-order traversal. You just sort it in n log n time, which go us. I mean, we could already do that with merge sort, but we have another n log n sorting algorithm. But the main advantage, the selling point on BSTs, is that we can maintain sorted order in log n time, even when the data is changing. And I always like to think of a leaderboard. If I have a global leaderboard of a game with millions of players, and it's constantly changing. Everybody's scores are constantly changing and they're moving position. With a BST, when somebody updates their score and I need to move them up the leaderboard, I remove that node and then add that node, and we can remove and add both. I haven't talked about remove, but that's 250's job. We can do both of those in log n time. Remove, insert, and find all in log n time. So we can maintain sorted order and changing data in log n time. With an array, inserts taking O of n. With a linked list, it takes O of n to go .next to find where we need to insert or delete. So that's our advantage. If we have dynamic data that we need to maintain sorted order, BST shines. And our algorithm really cut down the number of checks that need to be made. We have 7 nodes in this tree, and we only need to check 3 nodes to find out if a value exists. And even if the value doesn't exist, we're going to reach null after 3 nodes being checked. And the height of our tree was 3. We're checking the height of the tree, number of nodes, to be able to get to the bottom, to do our log n algorithms. But that doesn't cut it down much. From 7 to 3, big deal. What happens if we have 1,000,000 nodes, though? How does this scale? We have a tree, a BST with 1,000,000 nodes, and we need to go left, right, zigzag through this whole thing, and maybe we're trying to find an element that's not in this tree. And we have to go all the way down until we find null. How many nodes do we have to check? Just 20. So we take the log base 2 of 1,000,000, and that's actually a little less than 20. It's 19 point something. 20 nodes to get from the root of this tree to any node in this tree. This is, if you ever played the 20 questions game, this is how you can think of just about anything. And in 20 questions, 20 yes or no questions, it's zigzagging through a tree like this and getting down to whatever you were thinking of. A million different things you can be thinking of, and it gets to your thing with 20 questions or sometimes less. Because it's a binary tree like this, it can have 1,000,000 things.